Hello everyone. Today we are going to discuss the torque acting on a current carrying loop in external magnetic field which is uniform, right? So I have already drawn the diagram to show the construction, what is the setup. Now here this is a rectangular coil. So let's consider, suppose this is the coil. This is A, B, C, D. Consider it as a wire like this. Okay. So this means this is A, B, C, D. Now this is kept between two magnets north south so that the direction of the magnetic field is from left to right. This may be a part of horseshoe magnet, or this may be a complete bar magnet on this side with north on this side and complete bar magnet on this side with this S on this side. So now this coil is kept here. Now to allow the current to flow, we have attached a battery over here, so which is flowing the current in this direction, so from A to B to C to D. Now let's recall a case when we used to discuss the electric dipole. We used to have the net force on the dipole 0 in an external uniform electric field, right? But there was a torque acting on it depending on the orientation, right? So we are going to calculate this in case of magnetic field. So later on we will realize there are some similarities between the electric dipole case and the magnetic dipole case when we are concerned with the equilibrium. But for now you need to understand this structure. I hope you understood. There are split rings here. We don't need to go into detail over here for this. And we have an axis about which this will rotate. Now we already know that what is the formula for the force acting on a current carrying wire, magnetic force acting on a current carrying wire. So we know that formula ILB sin theta, that means IL cross B, right? So every part of the coil we will consider and we will calculate the force acting, magnetic force acting on every part A, B, B, C, C, D and DA, right? Now here in this case we are first considering a specific case where the plane of the coil is parallel to the magnetic field. So we are first considering that the plane of the coil is parallel to the magnetic field. So what will happen in that case? So parallel means, suppose I told you, as I told you, that this is the coil A, B, C and D. Now this is the coil and this is kept like this. Suppose this is your north pole and similarly on the other side we have a south pole. So this is the magnetic field is from left to right with respect to you, and the plane of the coil is parallel to the magnetic field. That means this plane is parallel to the magnetic field direction. I hope you understood this. So if you look at the top view I'll draw in another diagram. So first of all, when the plane of the coil is parallel to the magnetic field, we are finding the force acting on every part of the coil. Let's consider that this is the force acting on this part, this is the force acting on this part, F3 is the force acting on this part and F force is force acting on AD part. Let's recall, if there would have been only BC, we know that the direction of magnetic field is this is B, this is C. Now if you apply the Fleming's left hand rule, this is the direction of force, this is the magnetic field, this is the current. Now in this part, BC part, we have the direction of current like this, right? And the magnetic field is also in this direction. So if we know the formula that magnetic force is ILB sine of the angle between B and I, right? So here the angle between B and I is therefore this force, which is denoted here by F3, will be 0. Similarly, if I am talking about AD, the direction of current is like this, and this will be sine 180 because this is the direction of magnetic field and the angle will be 180. So therefore F4 is also 0. Now if I am talking about F1, let's check. This is the direction of magnetic field, this is the direction of current. So what will be the direction of F1? It will be normally outward from the plane of the board. So I can say that F1 is in normally outward. So I can write that on CD, this is the direction of magnetic field, this is the direction of current. So what will be the direction of force? This will be normally outward. So this is F1 is equal to I. What is the length? If I consider that this length is B and this coil is taken equal to this, so this length is B and this length is A, right? So instead of length, I am putting this formula. For length I am writing B. For which part? CD part. IB sine of 90 degree because the angle between the current and the magnetic field is 90 degree. So this makes it IBB. Similarly, we can find the force acting on AB part. So if I am talking about AB part, this is the direction of current, this is the direction of magnetic field, right? What will be the direction of force? This is magnetic field, this is current. So magnetic force will be normally inward. Look at this, normally inward. So normal, because my thumb is in the inward direction, this is the direction of current, this is the direction of magnetic field. So this is inward. So I will write down that the force on this will be normally inward. So this is outward, this is inward. So what will be the value of this force? This will be F2 is equal to I. Again the length is B, magnetic field is B, and here also this is sine 90. This makes it IBB. But these forces, if you look at the top view of the coil, now this is your ABCD coil. If you look at the top view, right, so this force will be, F1 will be this way and F2 will be this way, because this is taking it upward and this is taking it downward. So this is outward, F1 is outward and F2 is inward. So if you look at the top view, you will feel that this is moving anti-clockwise. This is moving anti-clockwise, right? So I will say that F1 and F2 are separated by some distance. So if we look at the top view, we have some space over here. So the top view shows that this is your top view of the coil. If this is B, this is C, right? And this force is upwards. And this is inwards, so you can say that this is, I hope this is visible here. This is not visible. No, it is visible. Right? So this means this is resulting in anti-clock movement and this is also anti-clock movement. Now there will be rotation about this center point. I can consider this as O, and the distance of O and B I can consider A upon 2, and this distance is also A upon 2, right? So how will I calculate the net torque? These two forces will result in a torque, and torque is equal to the total anti-clock torques. So this is F1 into perpendicular distance plus the other force into perpendicular distance. This is equal to F1 into A by 2 plus F2 into A by 2. So this gives me F1 is I, B, B into A by 2 plus this is also I, B, B into A by 2. If I add, I will get I into A into B into B, and this A into B, this is what? A is the breadth and CD, this is the length. So A into B, this is length into breadth. So this gives me area of the coil, right? So this was the first case when the plane of the coil is parallel to the magnetic field. Now I am going to tell you what will be the case when the plane of the coil is at some angle. Makes an angle theta with the magnetic field. So what will be the case like? Now initially I told you that this coil is parallel to the magnetic field. Now this coil is suppose making some angle with the magnetic field. Now this is the case. Initially this was the case, now this is the case. It is making some angle with the magnetic field. So if you look at the top view of the coil, this will be like this. Now B, C. Now in this case, there will be some force F3 and F4 in this case also, but F3 and F4 will be collinear. If you look at, sorry, this in this figure I can't draw this. This is normally outward. And this is normally inward. So that means, and on the these are on the axis of rotation. Normally outward, normally inward, but these are along axis of rotation, that is collinear. So if suppose I am talking about this is the force F3 and the other force is on this is force F4. So what will happen, these will be collinear along the axis, sorry, this way, this and this. So this will be collinear, so these will cancel each other, therefore no contribution to torque. But if I talk about F1 and F2, still F1 and F2 will be opposite to each other and these will be separated by some distance. But now the top view I am drawing here again, because here the diagram will be messed up. Now if this is C, this is B, if I am looking at the top view, the magnetic field is along this direction. Now this term I am going to explain what is magnetic moment. In this diagram, if I talk about magnetic moment, this is the direction of magnetic moment which is normal to the plane of the coil, and here the direction of the magnetic field was this way. So these were perpendicular, but in this case the magnetic moment is making an angle theta with the magnetic field. Now this is A upon 2 and this is also A upon 2. But if I am talking about the direction of the forces, in this case the force will be this way and in this case the force will be this way. Now what is the perpendicular distance between the force and the axis of rotation? If you look at this perpendicular distance will be A by 2 sine theta, and this perpendicular distance will also be A by 2 sine theta, right? So since the perpendicular distance is now smaller, previously it was A by 2 from point O, but now this is A by 2 sine theta. So if I find the total torque, what will it be? Torque will be force into perpendicular distance, that is A by 2 sine theta, and for second force it will again be A by 2 sine theta. Why A by 2 sine theta? What is the relation between the hypotenuse and perpendicular? The relation is sine theta. So that's why this is A by 2 sine theta. So if I look at the formula, this will be F1 value we know, this is I B B into A by 2 sine theta plus I B B A by 2 sine theta, right? So from here I can write down torque is equal to half plus half is 1. So this is I into A into B sine theta. So if I look at this part, this will be area of cross section of the coil, area of the coil. So this will be I into A into B into sine theta. Now I am going to define a new term for you, that is magnetic moment. This is denoted in the figure by M. right? So what is the formula for magnetic moment? This is I into A into number of turns of the coil carrying current I. So if a coil is carrying current I, then the magnetic moment direction is given by right hand thumb rule. So this is given by right hand thumb rule. So curl of fingers gives the direction of current in the coil and thumb gives the direction of magnetic moment. So in this case, if our coil is having this direction, so magnetic moment will be normally invert the plane. So if I look at the top view, it will be this way. So here I can draw this. This is normally inward, right? So this is for n number of turns. Now if I am talking about one turn, here I had taken only one number of turns. So here in this case n is 1. So for n turns, here I will just mention for n turns. What will be the formula for torque? For n turns, the torque will become N I A B sin theta, and N I A can be replaced by M, which is magnetic moment. So this will give me M cross B if I want to write it in vector form, right? So where torque is in a direction which is perpendicular to the plane containing M and B, which I have shown over here. Torque is perpendicular to magnetic moment, which is inward, and magnetic field, which is from left to right in this figure. So torque is perpendicular to M and B both, right? Now we can discuss about the maximum torque and minimum torque also, so that you are able to relate it to the electric dipole case. So for that I need to rub the board. Cases. Case 1. If theta is equal to 0 degree, then torque is equal to, theta is what? Theta is the angle between magnetic moment and magnetic field, or you can say the torque will be MB sin 0, that is 0. If case 2, if theta is equal to 90 degree, then torque will be MB sin 90, that is MB, which is maximum torque. Now here let's consider this. I had taken the horizontal coil here, right? When the coil is horizontal, that means it is parallel to the plane of the magnetic, its plane is parallel to magnetic field. In this case, the torque will be maximum, right? So if the torque is maximum, that means when the magnetic field is parallel to the plane. That means if your magnetic moment is this way, downward, so magnetic field is perpendicular to the magnetic moment. In this case, the torque is maximum. This kind of condition is called as radial field. So when B is perpendicular to magnetic moment, this results in radial field, which we will use in many cases, right? So I hope you understood this topic. This is slightly technical, but once you understand the concept step by step, it becomes very, very easy, and we have to use this concept later on in the topic moving coil galvanometer. So that's all for now. Have a nice day.